Oh, 1 second. All right. Hi, everyone. Before I begin the live stream today, I'm just going to be doing a couple of questions, one on center of mass and another one on the stuff that you should have watched the video on Tuesday, which is the kinematics of rotational motion. But before I, excuse me, before I start that, I just wanted to say something about next semester. Um, I really didn't want to have to do this again where I taught online like this. I don't like teaching online. I don't think it's the best experience, but it just seems that that things are not changing. And the college is again under the orders of New York State. And I don't know all the details, so don't quote me on this. Is again reimposing restrictions. And I was just kind of hoping this would be all over with. And so I think it's going to be online again. Well, no, I shouldn't say I think. It's going to be online again. But I wanted to make a couple of changes. The first change is the number of people that actually show up for the live streams is pretty small. Okay, and I think that's because they're recorded. You can watch them later. I don't blame people for that. One of the advantages of an online course that there is a time when you're supposed to be doing these things, but you can wiggle it around a bit as long as you're like strict about the due dates, like tests and assignments and so on. You're pretty good to move it around, and I want to give people that flexibility. That's a positive of these kinds of courses. The negative is that our interaction is just so tenuous. It's so rarefied. You just see me here as like on the screen. I'm kind of live, but I'm 30 seconds delay. You can ask questions, but you're asking questions through chat. I thought about Zoom, and there's others too, but students tend to be silent there too. It's just the very nature, the fact that we like being like physically together in a classroom when we teach. I think students like that, and I like that. So here's what I was thinking. This is not written in stone. I'm putting it out there right now, and just for feedback. I'll probably email this out too. But I'm thinking that I'll do pre-recorded lectures for the whole week, and actually schedule 1 week, one evening out of the week where I will physically be at the college, and it'll just be tutorial. It'll be optional. You can you can come there or not come there. And if people come there with questions, then I'll answer your questions. If people come there without questions, I can produce questions on the fly. That's what I used to do for students before the whole COVID thing. And then I think we would have the best of all worlds. And I would still do for those evenings that I can, the Google Hangouts. So, the only thing that would go away is the live chats. They'd be replaced with pre-recorded lectures. We would you would have the option of seeing me physically in front of a blackboard, or I guess a whiteboard with marker, and ask me questions there, or through Google Hangout. So the second semester is a bit different. The topics are a bit different than this semester. This semester is very logically demanding. It's believe it or not, we only covered 5 topics in the entire course. It's just that every topic is very elaborated. Next semester is a lot more smaller individual topics, and it turns out that you don't need as much tutoring for how to solve the problems as you do for this. I mean, you need a little bit. Don't get me wrong, but when you see, like, you don't have to see the same kind of question done several times. You generally get it when you see it once. So it's seems a little bit more justified to give only pre-recorded lectures there, and but still make myself available to you as much as possible, so that if you don't understand something, and that here's the thing with students, you don't know that you don't know, so you don't know if you don't understand something. So there's lots of reasons to try to have contact with me, and students will sometimes think they understand something when they don't, and then they find out on a test or something like that. So still make myself available for interaction, but instead of like interacting through a live chat, which is in this rarefied form, to have interactions actually in the classroom, optional, so you don't have to go there, but there it is. And think about it. Nothing is decided. If you say, you know what, I like this format, fine. If you have other ideas, I'd be willing to consider them. It's got to work for all of us, and so if it doesn't work, maybe I can't implement it. But if you can, I don't see why. I'll suggest it to people. I just thought that now would be a good time to present this to the class. I'm not going to get used to this new abnormal. I think this. Sorry, I'm going to just go off on a bit of an aside here. I really think that this whole COVID thing's got to resolve somehow, because humans don't interact well this way, and I don't think I'm just speaking for myself, which is why I'm saying it out loud. I think it would have been best if we had were physically together. But okay, there it is. So let me just look in the chat here and see. Okay, 6 people, and all right. Well, there was my little spiel at the beginning, and think about it, and I'll email it. I can even email out the syllabus early to see what people think, like a tentative syllabus. But basically, it would just say the live streams are removed, replaced with all pre-recorded lectures, one evening a week together in a physical classroom, and otherwise everything else the same. I think maybe the only other thing I'm going to change is I have to be very uniform with the rules with everyone. So if I say, the test date is this date and no other date, and people miss that test date, well, then there's a problem, because people make decisions based on that. So I can't give exceptions. That seems rather harsh. I think what I might do, and I'll build this right into the rules, is if you miss a test, then for every day that you miss it after, maybe up to 5 days, you lose it'll decrease the maximum that you can get by 10%. Okay, and then after 5 days it just goes to zero, something like that. I haven't thought about it that deeply yet. The reason for that is that just in case someone misses it on one day, I mean, not counting emergencies you're fine, because it's an emergency. But if you miss it because I don't know, you didn't read one of my emails in the morning or something like that, I could soften that a little bit. But the rule has to be the same for everyone, and you can't bend the rules halfway through the game, because if you bend the rules halfway through the game, then other people are going to say, well, why did you do that? And if I'd known that you were going to do that, then I would have made this other decision. And so that's why it's I have to be as strict as I am. It's not that I want to be severe. It's that you have to be consistent. It's a question of consistency, not severity. So this might not even affect you. You might say, well, why are you telling me this? I was on time with everything. Yeah, I know, but there were some people that weren't. And it's the nature of these internet classes that people tend to be a little bit more disconnected from them, and so uh, they'll tend to forget about them for a few days, and then those few days might have been the day when there was a test. You might wonder why in my emails I keep repeating the same thing over and over and over again. Well, that's why I do it, so that people have less and less reason to say I missed that. If you repeat for over a week that something is coming up and then you miss it, you say, well, didn't you read your emails for a week back? So anyhow, all right. There it is. Okay, so let me know what you think. I mean, I will send out an email probably next week asking for feedback that way, and we'll go on from there. Okay, so let's do our first question. Our first question is a center of mass problem, and let me just read it for you. So let me move this up a bit. Yeah, okay, you see all the numbers there. Okay, so find the center of mass of the following system of masses at the given locations, okay? So first of all, what's the center of mass? Well, like we're moving into this rotational motion, and the center of mass is a special point because if you take some object and you throw it up in the air, you see what it spins around its center of mass. Or you take an object and you balance it along the middle, and we'll see this is our first topic next semester actually, is statics. You balance something in the middle, you've got your finger right under, like, here's my remote here, you put your finger under it like there and it balances. I'm not going to get this right, but you got the idea. Okay, well, your finger is right under that center of mass. Okay, so this center of mass is a special point, and it's kind of like a weighted middle of it. Okay, now like in the assignment, if you finish the assignment, I give you two center of mass problems. One's 1D and the other one is a 2D problem. We're going to do a 2D problem, and the 2D problem, I actually give you a picture of it. I tried to give you a picture using an ASCII drawing, but you don't really even need that. Okay, so in this problem here, it's about as abstract as I can make it. I just literally give you the numbers. I've got a diagram which I'll show at the after we finished it, but here's the numbers. And you know what, I probably shouldn't have used this notation here. Let's just say that this first number, this is x, so this first number is the x coordinate like that, and the second number here is the y coordinate like that. Okay, so we haven't used this bracketed notation this semester, so maybe I should just be consistent there like that. So I wasn't thinking to be consistent with my notation when I wrote the question, but generally, like in my questions, I've been saying x is equal and y is equal, and so let's stick with that. Okay, so for each one of these, I give you x and y coordinates like this. Okay, and I ask for the center of mass. All right, so the way this works is that like all of our problems in Cartesian, once it's in Cartesian, the x stuff is calculated purely independently of the y stuff and vice versa. Okay, and so here's the equation and the solution. Actually, let me just cut and paste the x and y. They really are pretty easy, so there's not much for me to say, and I see that I lost my I think this is going to happen a lot. This when it starts happening, it doesn't seem to want to stop. Okay, there we go. So over here, let me just scroll up a bit. Here's the formula for the x direction, like that, and it's numerator divided by denominator. It's a little hard to see. Here's the numerator, and here's the denominator. Okay, in the numerator, you simply add up m times x component of all the masses, and in the denominator you just add up all the masses like that. Okay, this is in what's in statistics. In statistics, this is called a weighted average. Okay, and it's kind of like how you calculate grades, and of course some things might be weighted more than other things. The weighting are the masses, and the things that you're weighting are the x components. Okay, so in the numerator, m1x1 plus m2x2 plus m3x3 plus dot 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 means however many you have here. Okay, and then in the denominator, m1 plus m2 plus m3. In our case, we have an m4, but I put dot 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 there to indicate that it's as many masses as you have. Okay, so we have 4 masses. So here's the numerator. It's 3 kilograms there. You see that? Okay, so 3 kilograms right there. And you just pick out the x component there like that. There it is. Okay, and then m2 is 4, and x2 is 0.95. Okay, and then 5 kilograms here, and then 2.5, and then 1 here, and then negative 0.5 there like that. Okay, and then in the denominator you just add up all the masses, 3 plus 4 plus 5 plus 1, and that gives you an x component of 0.742. Okay, so there's that. All right, now the y component, how do you calculate that? Same formula, except now your x's are replaced with y's. Okay, and so here is that formula there. And the next line is not a typo. I didn't mean x here. What I'm trying to indicate in that line is that it's the exact same form as above, so you would do the same calculation, but where you had the x's above, see how I have the blanks in there? there you're going to replace the x components with the y components. Okay, so the x component for the 3 kilogram mass was negative 1.3, but the y component is 1.4. See right there? Sorry, right there, y 1.4. So y component 1.4, y component of the 4 kilogram was negative 1.3, y component of the 5 kilogram is 0.15 and negative 1.5, and then crunching all that through, you get negative 0.135 for the y component of the center of mass. Okay, so we have an x component there and a y component. Now that was very abstract. It was just like literally just like plugging into equations. You might wonder, what did you just do? What did we just do there? Well, I did it this way on purpose without showing you a diagram, because you don't really need the diagram to do the calculation. But let me show you the diagram. It's just a very rough drawing of like where things are. So all I did was like, I just said, oh, 3 kilogram is at x is equal to negative 1.3 and y is equal to positive 1.4, and so on, and I drew it out. And here's what it looks like. So there's the 3, there's the 4, the 5, and the 1, like that. And if I asked you, where do you think the center is here? You might say, well, I don't know, it looks like there. But then it's not so much where the center is. It's where the center is, but weighted. So that 5 kilogram tends to pull the center of mass a little bit closer to it, and the 1 kilogram less. Okay, so the 5 pulls it more, and the 4 a little less, the 3 a little less, and the 1 hardly at all. And so what we found was, let me see what the numbers are. It's like the x component is 0.742. So over here, let me do this in blue. This is like 1. It would be somewhere along this line here, like this. I'm trying to draw a line about 0.75, 3/4 of the way over, like that. Okay, and then the y component turned out to be, it turned out to be negative 0.135, which is very close to 0, so somewhere like along there. Okay, and so where do the two meet? Right there. There's your center of mass. Okay, and if you look at that, you could say, yeah, I could see how like it's being pulled a little bit closer to the 5. It's closer to the 5 than it is to the 1, and the 4 is pulling it a little bit closer than the 3, and so on. And so yeah, that kind of makes sense. Okay, if you had seen that the center of mass turned out to be like, I don't know, like, first of all, if it's like outside of like, like these things sort of form a, they sort of form a shape here like that. If you had found that it was out here, that's totally wrong. It can't be outside of like the middle of the shape. Okay, but if you have found it like here, you might say, wait a sec, that looks like it's being pulled to the 3 more than it is to the 4 and 5. So yeah, kind of makes sense. All right, so there we go. I mean, a very simple problem, but I thought I'd show you how it's done. Let me take a quick look in the chat here and see. I like the idea of being able to have at least 1 week for questions and practice. Yeah, absolutely. Yeah. I don't. To answer. Josh asks a question. He likes the idea of being able to meet at least once a week for questions and practice. Absolutely. I wouldn't just remove the and at least you too. I wouldn't just remove the live streams and not replace them with something. So the idea is to kind of remove the live stream, but replace it with like a physical time when we can be together. So you're like, imagine instead of us doing it this way over YouTube, that we're actually doing it face to face. But I would be doing the same thing. Okay, there are more smaller topics next semester, so more. More pre-recorded lectures would probably have to happen anyhow, but yeah. All right, so thanks for the feedback. But I'm not seeing any questions about the center of mass, so let's move on to, and I lost it again. That's okay. Here we go. Yeah, less technical problems when you're face to face as well. Okay, so the next one is on our last topic, or the first half of our last topic, which is rotational motion. And let me just briefly remind you what I said during the pre-recorded lecture. There's like with rotational motion, everything that we've done previous to rotational motion kind of assumed that the mass was just a point. I mean, I didn't draw, when we did Newton's laws and blocks sliding down planes, I didn't draw them as, dots, but we treated them like dots. If you remember, we put all the forces at the middle. We actually put all the forces acting at the center of mass, and we didn't worry about the extension of the object. But in reality, there's an extension, and when there's an extension, it means that things can rotate. They rotate around some axis. That axis, if it's free, if I throw something like I just throw it up into the air and it rotates, it'll always rotate through around an axis that goes through the center of mass. I can, however, force it to rotate around an axis that doesn't go through the center of mass. I mean, I could literally put a stick at one end or just grab it like this and force this thing. The center of mass of my remote here is probably in the middle, but I could just grab it at the end and force it to rotate around that. Okay, so rotational motion that we study is quite general. It could be around the center of mass, which is what happens naturally when you throw things, when things are free falling or free motion. But it could be like a door around hinges or anything like that. Okay, so I picked this example because this is one that comes up in biology. Centrifuge. So a centrifuge is this was the numbers I have here are off of something I found on Amazon. I just looked up centrifuge on Amazon, and because I don't know what numbers to use. And a centrifuge is basically you put test tubes in this thing and it spins. And when it spins so much that it produces a lot of centripetal acceleration. And if you've got something like human blood in there or some sample, it'll separate it out into different layers. Okay, because the acceleration gets really big, and so that's what inspired this question. Okay, so I have a centrifuge and it starts from rest, okay, and I turn it on and it spins up to 5,000 RPM. Okay, and it takes 45 seconds to do that. Now, all these numbers are actually real. I took the 45 seconds. I don't know. I couldn't find that on there. I made that up. Okay, but let's just assume you turn this thing on. It takes 45 seconds from rest and it spins up to maximum speed in 45 seconds. Okay, which is 5,000 revolutions per minute. That's what that RPM means. Okay. The bottom of the test tube experiences an acceleration of 3,74 G. Okay. Now with G, you say, what is that? That's just the acceleration due to gravity, and that's 9.8 meters per second squared, but we'll round it off to 10. Okay. So whenever you see someone says, oh, the acceleration was like 5G, all they mean it was 5 times 10 meters per second squared, or 50 meters per second squared. Okay, so the bottom of the test tube experiences an acceleration of 3,074 Gs at maximum speed. Okay, so here are the questions. What is the angular acceleration? Okay, so the angular acceleration, let me show you all the formulas that are involved here. I guess I should say here, assume constant angular acceleration, like that. Okay, so if you assume constant acceleration, then you can make use of these formulas. And what are they? They are these ones. Copy. And I lost it again. This is going to happen every time I switch between windows, but like I said, I know to look for this. So, okay. All right, so what are the equations? Well, there's this one, and you may say, that doesn't quite look the way you wrote it, maybe in the pre-recorded lecture. Well, in the pre-recorded lecture, what I had is theta is equal to 1/2 alpha t squared plus omega, times t, I forgot a t there, plus theta naught. But if you bring the theta naught to the same side, so you put the theta and the theta naught on the same side, what you wind up getting, maybe I should just show you that very quickly. Yeah, I don't want to confuse you. This is the way I would have had the formula written, like this. Okay, in the lecture you saw. Okay, and that equation should look very familiar, because what is it? It's the 1D kinematic equation for constant acceleration. Okay, it's the exact same mathematics, but now applied to rotational motion rather than linear motion. And you could use the equation this way, but generally we don't measure angles directly. We measure changes in angle. So if I subtract theta naught from both sides, like this, so I got theta minus theta naught from both sides, I get this equation. And then I could say, well, but what do I mean by theta minus theta naught? Well, that is just delta t. That is just your change in angle, okay? And so this is, that's that equation that I just had. It basically says the change in angle over some time t is going to equal a half times alpha, and alpha is the angular acceleration, t squared, plus omega naught, that's your initial angular velocity, times t, like that. Okay, and that's one equation. Call that, I guess, that we did call it equation one, like that. Then there was this one. This one was equation two, and it's basically omega is equal to alpha t plus omega naught. And now what does this say? This basically says, after if you've got some constant angular acceleration alpha, after some time t, you're going to be at an angular velocity of omega. If you started off with an angular velocity of omega t. I didn't say that so well. Let me say it again. You start off with an angular velocity of omega naught, and then after a time t, you'll be at an angular velocity of omega. Okay, and then the last one is basically 1 and 2 with the time removed, like that. Okay. All right, so what is the angular acceleration? So you say to yourself, well, what do you have? Well, I did give you the time, okay, 45 seconds. All right, so you say, all right, I guess I could use either 1 or 2. All right, you want to find alpha, so that's unknown and that's unknown, but that's okay, because that's what you want to find. You have t. Omega naught, do you have that? Well, it says that you started from rest. And omega is this angular velocity. It means how fast something is spinning. Well, before you turn it on, it's not spinning at all. Okay? So omega naught is 0. After it spins up, it's spinning at 5,000 revolutions per minute. Okay? And so that's your omega. So you have omega naught, you have omega, you have the time that it takes. So you have everything except for alpha. And so you could use number 2. You don't have that change in angle. Like, you don't know how many times this thing turned as it was spinning up. So number 1 you can't use because you don't have delta theta, and you don't have alpha, and so you can't use number 1. And number 3 you can't use for the same reason. You have neither alpha nor delta theta. Okay, so we're going to use that equation right there. All right, and here's what I got. Did I lose the? Yep, every time now. Okay, I see how this works. All right. So here's my answer to part A. So just repeating what I said, the initial angular velocity. So this word angular velocity, like it is the correct term, but it just means how fast it's spinning. And how fast is it spinning initially? It is at 0. Okay, the units are radians per second. All of these problems, to work out with the formulas I gave you, you have to work in radians. Okay, and if there's anything tricky about the problems, is making sure that you're in radians per second or radians per second squared. Okay, so 0 radians per second that's easy. What does it spin up to? What's the final angular velocity? It's omega. Okay, and that's 5,000 RPM. I say that in the problem, but RPM, that is not an MKS unit. Okay, RPM means revolutions per minute. I've abbreviated that to rev per min, but yeah, revolution means turn per minute. So you could say revolution per minute. You could even say turn per minute. Okay, like how many turns does it make in 1 minute? All right, so this one makes 5,000 turns every minute. All right, which is pretty fast. I mean, these things, I don't know if you've ever worked with a centrifuge in like a biology lab or maybe even in chemistry, but they tend to be used more in biology. They really spin. You hear these things really, really whirling in there. Okay, so this is 5,000 turns per minute. Okay, but how do you convert that? And, I showed you that in the pre-recorded lecture. So we have revolutions in the numerator. And so we want to get rid of revolutions. So I guess I'm looking at this one right here first. So revolution, to get rid of revolution, we want to go from revolutions to radians. Both of them are measures of angles. And so 2 pi radians, that's 1 turn, right? So 2 pi radians is 1 revolution, okay? And you put the revolutions in the denominator here because it's in the numerator over there, okay? And the minute to seconds, that's easy. Minutes are in the denominator, so you put minutes in the numerator divided by 60 seconds, okay? And so to convert, basically, you take 5,000, You divide by 60 and you multiply by 2 pi, and it gives you that number right there. Okay, so roughly speaking, it's like dividing by 10, a little less, okay, but it's like dividing by 10. So if you have 5,000 revolutions per minute, that turns out to be roughly 500 radians per second. Well, a little bit off, but it's 5,023.6 radians per second. Okay, so yeah, I do give you the final velocity, angular velocity, but not in the right units. Now it is in the right units. The time was 45 seconds, so we're going to use equation number 2. Plug into equation number 2, and it's easy to solve, and there it is. Okay, so it's 11.6 radians per second squared. All right, and that is your angular acceleration. All right, and let me switch over here, see if there's any questions in the chat. Nope, everyone looks like you're doing okay. And let's continue with part B then. Okay, so how many times does it turn during the startup time of 45 seconds? Okay, so in other words, you know, I turn this thing on and it spins once, twice, 3, 4, 5. But you know, it starts to spin slow and then faster, 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 faster. But still, after 45 seconds, how many times has it turned? Okay, and you say to yourself, geez, you know, which one of these quantities up here, back in the, you know, the equations here, I guess these ones right here, okay, in these equations, which one is the number of turns? And it's not obvious that is the angle, because you see, you think of a turn as like a complete turn, but you know, an angle is a turn, because you know, if you have like a quarter of a turn, that's like a 90-degree angle is a quarter of a turn, you see. Or in radians, that would be pi by 2, okay? Or you know, half a turn, that's 180 degrees, or pi radians, okay? Or a full turn, that's 2 pi radians, or 360 degrees. So whenever you hear the word turn, you probably didn't associate in your mind that when you say a turn, you're really talking about an angle. Like you could say, you know, 2.5 turns. What does that mean? Well, once, twice, and then another 180 degrees, you see. So turn in degrees and angles, a turn is an angle. Okay, so when you see a question that says how many times did it turn, read that as what angle did it turn through. Okay, so you know, if I hadn't said that to you, you might have found it tricky, because your brain thinks in various categories, and it thinks of turns as turns and angles as angles, and never the two should meet, but they're the same thing. Okay, they do meet. Okay, so how many times has it turned during that 45 seconds? So I'm really asking for delta t. Okay, I'm at delta theta, because that is the number of turns. Okay, so theta naught is like your initial angle and theta is your final angle. The difference between the two is how much it turned. Okay, which is why I wrote the equations the way I did in terms of you know, delta theta. All right, so you could either use number 1 or you could use number 3. Okay, I don't know which one I used actually. Both of them will work now, because you have everything you need. Like you have you know, you have alpha now, so you could use number 1, and you could use number 3 as well, because you have alpha. Let me see which one I used. Over here, I'm just going to cut and paste my answer. I used number 1. Okay, but if you want, you could check on your own and do it later with number 3, and see that you get the same answer. If you don't, then we did something wrong. Okay, so the turn, delta theta, is equal to 1/2 alpha t squared plus omega naught, and I forgot the t again. There it is, like that. Okay, now plug in the numbers. Well, a half is, you know, 0.5. Alpha, that's what we just found, 11.6 radians per second squared, and the t is 45 seconds squared. Okay, omega naught, the initial angular velocity, was 0, so 0 times 45 seconds is still 0. Okay, and that turns out to be 11,745 radians. Okay, now that does kind of answer the question. You know, if like if that had been one of the answers on multiple choice, that would have been correct. But I did say how many times has it turned, okay, or how many times does the centrifuge, yeah, how many times does it turn, okay? And so radians does answer the question, but indirectly. If you actually want it as a turn is a revolution, okay? And so you know, you might see a question like this on the test, or on the next week's assignment, and when you see the the question, it'll say how many times does it turn, and then it answers the number of turns, but you got it as an intermediate answer in terms of revolution, in terms of radians. So what do? Convert from radians to revolutions. Okay, so revolution turn means the same thing. Okay, so here 1 revolution divided by 2 pi radians. All right, and I put the radians in the denominator here because radians in the numerator there, and that'll make them cancel. Okay, so notice that's the exact opposite conversion that we did before. So here I'm going from revolutions to radians, whereas before I went from radians to sorry, here I'm going from radians to revolutions, whereas here I went from revolutions to radians. Okay, so we're going the other way around now. So that's why here it's 2 pi radians divided by 1 revolution, and over here it's 1 revolution divided by 2 pi radians. Same fraction, but it's reciprocal. Okay, and that just means take that number and divide it by 2 pi, and that gives you 1,869.3 revolutions. Okay, so there you go. That's how many times it would turn in 45 seconds. As I said, this is spinning really fast. Okay, so that's 1,800, a little over 1,800 turns in just the first 45 seconds. Okay, so it's really spinning. And all right, next question. What is the centripetal acceleration at maximum speed? So at this point, you might think, would I use one of these equations here? And the answer is no. I actually give you the centripetal acceleration, but in an indirect way. Okay, and let's read the question again. You'll see that it's actually in there. All right. So it experiences an acceleration of 3,074 Gs. So when this thing is spun up, okay, and it's no longer accelerating angularly. In other words, so angular acceleration is how much is it speeding up? It starts turning slow and then goes faster, 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 faster. Okay. The centripetal acceleration, even once it's spun up and it's not turning any faster, it's always turning at that 5,000 RPM. Okay. The angular velocity isn't changing. You still have the centripetal acceleration. Okay. So you remember when we did uniform circular motion? Uniform circular motion was the centripetal acceleration is the acceleration that keeps you on the circle. Okay, and so that number there, that 3,074 G, that is the centripetal acceleration. Okay, so when you look at these centrifuges like Amazon.com or wherever you might want to buy them from some biotech company, they'll tell you what the centripetal acceleration is. Okay, that's kind of their rating. So that means that objects in this test tube, they're going to weigh 3,000 times more than they would if they normally. Okay, so if you were inside this test tube, you'd weigh 3,000 times more than you would normally weigh. By the way, we can barely stand. We pass out at 9G. Okay, so at 3,000 Gs, you'd be crushed. All right. So I pity any bacteria that might be in that test tube. Okay, so so the centripetal acceleration. Don't try to use one of those formulas. I gave it to you. It is that acceleration that is due to the spinning, and so AC is just going to equal, and I've got this worked out, so let me just cut and paste here. AC is just going to equal this right here, like that. Okay, it's that's 3,074 multiplied by G, 10 meters per second squared, and so it turns out to be 30,000 and some change meters per second squared. That's the acceleration. Okay, so acceleration due to gravity 10 meters per second squared. Acceleration in this centrifuge 30,740 meters per second squared. Okay, now the next one is a little bit tricky, and it asks how far is the bottom of the test tube from the axis. Okay, because that acceleration is actually obtained at the bottom of the test tube, and at this point you're going, geez, how do I solve this? You've got that centripetal acceleration, the angular acceleration, and you know the maximum angular velocity, and you go, well, is there a relationship between the two? And there's actually two accelerations that are involved here. There's the centripetal and the tangential acceleration. It's really the centripetal, it's the angular velocity that you want to relate to the centripetal acceleration. So you really want this right here. Okay, the centripetal acceleration is equal to r omega squared. The other one, which is the tangential acceleration, this one, is equal to r alpha, and I need an alpha, like that, okay? Is equal to r times alpha. And this one here is actually small, and it's not what we want in this case anyhow, okay? We don't want that because you don't know the tangential acceleration, okay, first of all. Secondly, once the thing has spun up and it no longer spins any faster than 5,000 RPM, the angular acceleration becomes zero because it's not speeding up rotationally, and that at that point the tangential acceleration is zero. Now the one that relates the centripetal acceleration to the angular quantities is the first one. It's this one, and the angular acceleration is actually related to omega. Okay, I'll draw a picture of this in just a second after I solve the problem to show you what the difference is between these two, because they oftentimes cause confusion. They are different formulas, they're very different quantities, they're actually perpendicular to one another, and people wonder, well, should I use this formula or should I use that formula? You want this formula right here. Okay, well, if you use that formula there, what am I asking for? I'm asking for how far is the bottom of the test tube from the axis. Okay, so you have to picture the test tubes in there, and there's a bottom of the test tubes, and they're far from this axis. There's a certain distance from the axis. I wouldn't say far, but there's a certain distance from the axis. That's the r that you want to calculate. Okay, and so rearranging this, r is going to equal AC divided by omega squared, like that. Okay, and we have those numbers. Well, let me just cut and paste the answer because I've got it over here. Here it is. And did I lose it? Nope, I didn't lose it. Okay, so what did I get here? So I've got, here's my AC that I have from the previous problem. There's my omega squared. That gives me 0.11213 meters, or 11.2 centimeters. I actually looked at the specifications, and I didn't see any specifications, but that looks very close to the right answer. Okay, I mean, I've seen these things physically, and they're about 10 centimeters. So the test tubes sit in there. They sit in a bit of a slant, but the bottom of the test tubes, the furthest point from the middle in the test tubes, is about 10 centimeters from the axis. Okay, so that's kind of neat that it works out. It works out right. Okay, so let me show you what the difference is between this angular, so centripetal acceleration and tangential acceleration. Okay, let me switch to this and create a new diagram. All right, so we have like this is like a point on the bottom of the test tube, like that, and that's a terrible circle, but just use your imagination a bit. And the center of this is somewhere in here. Okay, and there's two accelerations. There's an acceleration as the thing is turning and speeding up. There's an acceleration this way. That's the tangential acceleration. Okay, but at the same time, because it is on a circle, there is a centripetal acceleration, like that. Okay, now as long as this thing is spinning and speeding up as it's spinning, the angular acceleration is greater than zero. But as soon as omega becomes constant, that is, the angular velocity is constant, so when this is constant, that's supposed to say constant, then AT becomes zero. Okay, so when this thing is spun up to its maximum speed, this vector here goes away, and it's purely AC. Okay, so AC is the thing that's really doing the work of a centrifuge. Okay, the other the other acceleration, it's there, but it's not really part of what's causing the separation, okay, of the material. So let me get rid of that. Actually, I'll just redraw it for my next class. Okay, so it might be worth just looking at how big AT is. Okay, so I didn't ask this, but just to show you, while the centrifuge is spinning up, AT is equal to R times alpha, okay? And that's equal to, well, we know R now. It's this number here. And alpha we have from above. And my phone is ringing. And what's that equal to? That is equal to multiplied by 0.6. Yeah, it's relatively speaking a small number. Let me just round it off. Meters per second squared. Okay, so I mean, take a look at the differences here. So you've got a centripetal acceleration of 30,000 plus meters per second, and you have a tangential acceleration of 1.3 meters per second. Okay, so the tangential acceleration is there as it spins up, but like I said, it's tiny compared to the centripetal. Okay, let's see if there's any questions in the chat here, and then if not, we'll finish off the last question. Okay, and so the last question is, how fast? How fast is a point at the bottom of the test tube moving? So I'm asking for the tangential velocity, okay, and that's VT, like that, and VT is equal to just R times omega, like that, okay? So VT, sometimes students confuse VT and AC, okay, because the formulas look the same, but they're really quite different. AC is the acceleration towards the center, and VT is the velocity along the outside, along the perimeter of the circle, okay? And what's that equal to? Well, let me get that answer. There it is. It's 58.7 meters per second. Okay, so yeah, it's moving. It's moving quite fast. So 58 meters per second, just to give you an idea how fast that is. Oh, where did I get omega? Maybe I should just say that first before I finish off here. Omega is, we found that up above, right? That was that 5,000 RPM, and that was the 523 0.6 radians per second. So there it is, 523.6 radians per second. And so there's the velocity as this thing is turning. So if you were like a speck at the bottom of this test tube, you know, you're whirling around. If I said, how fast are you going? All right, not how fast are you spinning, but how fast are you going? It'd be 58 meters per second. In other words, like, even though it's in a curve along the circle, you know, you travel a distance of 58.7 meters every second. Okay, and that is pretty fast. Let me just quickly give you an idea what that is. 0.7. Let me convert it to kilometers. 3.6. So that's like 200 and that's like 211 kilometers per hour, okay, which is really, really fast, okay, and but you know, these things do turn fast. So one of the things, you know, when you close these things, when you spin them, you have to close them because they won't spin without that. Because if you had your finger in there, and could you imagine like something traveling that fast hitting your finger? So they do turn pretty fast. Okay, well that's it for the rotational motion, and that's all I wanted to do today. So if there's no questions in the chat, we can just call it a day. So I don't see any. Okay, so is everyone okay then? All right, I don't see any questions, so let's end the live stream right now. I know it's a little bit early, but we have lots of time by the end of the semester. This is our last topic. All right. Okay, bye-bye.